Hey, good morning, all. I revealed our first assignment yesterday, so I wanted to take the first minute or two of class and ask if people have any questions. First question I got a little while ago was, should we be modifying the same package or creating a new package? Doesn't particularly matter. If I were doing it, I would continue on in the same package. Everything that we have done so far exists as code on Canvas. So if something gets so horribly screwed up that you don't know how to undo it, you can always make a new one, import the code from Canvas and start fresh. That is the absolute worst case, and you would have the package as it exists today anyway. That's my reasoning for that. Any other questions people have about getting started with the assignment? My recommendation for it is to get started sooner rather than later. I give people a week because I anticipate that it will take most people a good chunk of that week with some back and forth between when you get stuck, have some time to come to office hours. Let me help you get unstuck. Continue to work, get stuck again, come see me again. That is anticipated, that's part of the process. It is not weird or unusual at all. Anything else before we dive into complexity analysis? This is a hugely important topic that will carry through the rest of your computer science education, and if you go into this field, the rest of your career. It is that important. While it's not directly on the APE, it informs many discussions that we are going to have about those concepts in ways that will help them to stick. So it makes way more sense to cover this first so that we can analyze everything that we are doing later in a way that helps you to understand it better. So it's worth the 2 to 3 days that we will probably spend on this. Any past experience with complexity? Anyone want to take a stab at what complexity analysis means within computer science? Yeah. Okay, I like that. Some parts working together. Yeah.
It's approximately how long.
Yeah. So how the runtime and memory scale based on the amount of input that we are trying to process. So the application to this is we have something like 2 competing algorithms. We want to determine which of them is better for solving a particular problem. That problem is going to be, I need to retrieve a value from a list. We've seen a couple of different list types at this point. We've seen an array list and a linked list. So which one are you going to implement if the goal is to very quickly retrieve values from that list? Yeah.
Array list.
Array list and why? Yeah, we have a direct access to every index in the list. And if all we need to do is a bunch of gets, a bunch of reading the list without modifying the list, the array list can get there very quickly, and the linked list is going to need to iterate starting at the beginning of the list. Are you what we're looking for? Are you what we're looking for? Or if it's a particular index, actually run through that loop that many times. So it's more work to do this in a linked list than it is in an array list. Does that mean that a linked list is worse than an array list? It's worse at get, but that's not the only thing that the linked list does. The reason we introduce many different types, or at least 2 different types of lists, is that there are pros and cons associated with each. We'll dive into exactly what that is, but how can we formalize this idea? How can we, in general, find 2 competing algorithms and analyze which one is better for a particular use case? One way you might do this, if you weren't familiar with exactly how these worked and you had particular implementations, maybe you're importing the array list and the linked list and you want to know which one to do, you could write a program and you could have both of those list types try to get an element in the list. We are going to go ahead and get the 5th element in the list. little small to see, but we just are going to make a linked list, make an array list. And then how we're going to do this is we're going to, basically, we take this before, that is we call system.current-time millis. And that has to be stored in a long because it stores the number of milliseconds since January 1st, 1970. Quite a few milliseconds have passed since January 1st, 1970. So we take a snapshot of what is the time right before we call this get. We call the get, and then we do the exact same thing with the after. Then we're going to subtract the number of milliseconds between after and before, and that tells us how long it took for the list to grab that fifth element. And we're going to do exactly the same thing for both lists. And we find, if we do this, that the answer isn't particularly helpful. First of all, a millisecond is a pretty fast period of time, 1/1000th of a second. So getting the fifth element of an array list and a linked list happened faster than 1/1000th of a second. So not particularly helpful. What did we learn from this exercise? Computers are fast. Doesn't really help us to make that decision about which is better. Any ideas? How could we fix this to actually give us meaningful data about which one is faster? Couple different reasonable answers here. Say 1 and then 2.
Instead of multiple or one get, you do multiple gets.
Okay, multiple gets. I like that idea. That is the way that we are going to do it, but there is one other that might be interesting. Anyone have any other idea? Yeah. Run it on a different machine? Yeah, this is machine dependent, right? Depending on the CPU, but I would expect that with any modern machine, you're going to get 0 milliseconds for both of these, regardless of the machine that you run it on. Even if it's a potato machine from 15 years ago. Okay, increase the precision. I'm not sure if we can go past milliseconds. That'd be a good idea if that functionality exists. I'd have to research it and figure it out myself. What do we know about, if we knew something about the structure of the array list and the linked list? We're getting the fifth element. Yeah.
We change the element that we're trying to get. So like instead of trying to get the fifth element, you try to get like the last element.
Yeah, you make a much longer list and then try to get the 1000th element or the 1,000,000th element or something that would actually take a linked list, maybe a little bit of time to actually get to, since it has to iterate from the head all the way through until it finds that particular index. So either one of those could work. We're going to wrap the call in a loop and get up the fifth element a bunch of times. The exact times, we talked about this, running this on different machines. It'll vary every time you do it. Why? There are other programs running on your machine that are vying for the resources that are associated with it. Small changes to exactly how everything works. So it will vary every time you do it by just a little bit. It'll vary per machine. Faster machines can, surprisingly, do things faster. We talked about getting element 50 rather than 5. That would exacerbate the issue because an array list, it doesn't really matter where we're looking. We have direct access to every index. With a linked list, we can only start at the head. So now we're going to run this 1,000,000 times. We're going to get the same element 1,000,000 times. Imagine if I did this to you on homework. It's amazing what we're willing to do to a machine that we're not willing to do to each other. Do this same useless task 1,000,000 times. Poor computers. When we do this, it's still pretty darn fast, but we're starting to actually see a difference now between the array list and the linked list. The array list takes 21 milliseconds to get the fifth element 1,000,000 times, and a linked list takes 39 1,000ths of a second to do exactly the same thing. So almost twice the time, but still lightning fast from yours or my perspectives. Computers are fast. What else can we do? So we talked about how an array list gets a value. It's just an add and a multiply. And a linked list is in a loop, iterating, accessing a memory address, accessing a memory address, accessing a memory address, accessing a memory address, and then accessing a value. So this is the result for getting element 50 instead of element 5. We can see that the array list took 1 more millisecond. That was just that random variation that we could expect. I wouldn't really expect it to take longer to get this index than some other index. But the linked list sure took a lot longer. It went from almost twice as slow to more than 10 times slower. Interesting. So did not take the array list more time to get that, because any direct access to a memory address is still just an add and a multiply. It doesn't matter what the values are in that add and multiply. It's capable of doing all of those at the same speed. On the other hand, the linked list had to iterate and do 10 times as much work, 10 times as many .next calls. It's only 4 .next calls to get to index 5. It's technically 5, we're starting at index 0, so it's 5 versus 50. So it is actually 10 times more work. So it makes sense that it's taking the linked list a significant amount of time longer to do that. We've also answered this question already. Does this mean that an array list is better than a linked list? The answer to this was no. It's better at getting, and it gets better and better at getting the deeper into the list you get. Relatively. If we were to get an index higher than that, we would expect that the linked list is going to take even longer, but we would not expect the array list to take any longer at all. So this tells us something interesting. The array list get is independent from this concept of which number we pass the get, what index we're trying to get from. It always has the same performance. Whereas a linked list does depend on the index passed, and it's going to scale how long we expect it to take with how far away from the head that query is. As a developer, we may want to ask a client. A client needs some implementation, and that turns out that we think we should make a list to do this. The client tells you that they're going to be filling this information once, and then their live service is going to be querying this list a bunch of times. If that is the case, then you might want to make an array list rather than a linked list, because the accesses are very fast, no matter how much data is being stored. So that would be a hint as to which equivalent structure to use. We know that both an array list and a linked list do exactly the same call, they have exactly the same concepts, exactly the same calls are possible with them. But now, as the engineer behind this, it is your job to make the decision about which of these equivalent structures to use. From the end user's perspective, it looks exactly the same. But from our perspective, the actual time that it takes to accomplish this will vary depending on the structure that we use. How are we doing this in general? So we don't really want to write programs all of the time to compare different algorithms running times to each other. So how could we be able to analyze this by thinking about them and using what we know about math rather than writing a program to do it? So we have 2 methods we want to compare. You can use as an example in your head the array list and linked list get we just talked about. If we did this for every possible input size, we could build some kind of table, and that table would tell us for a bunch of different input sizes, what are the associated running times. And that table would reveal how that number increases with respect to the index we are querying. With this data, we can do some kind of regression to fit some kind of mathematical function to the growth rate of this function. As the input or as the query grows in size, how does the running time change? What function best approximates how this algorithm is scaling, how the algorithm's running time is scaling? Once you have that scaling factor for both algorithms, we could compare the functions to each other to be able to make some kind of decision about which we should use. Now let's say those two methods have run, we've looked at the associated tables, and we've pulled out the following mathematical expressions. Method 1 takes 10n squared minus 5, where n is the input. And method 2 takes 100n plus 200. Maybe it's been a while, but go ahead and on paper and a text app of some kind, in a paint drawing app, whatever you want to use, go ahead and see if you can sketch what you think these two functions look like, overlay them on the same graph. So draw your own axes, draw your own scale. What do these look like?
You don't want to use a math lab, right?
No, you should use, this should be your own head, your own intuitive, what does this look like? I have an answer for you here momentarily, so we will get that. The outcome from this is how different is just staring at this and what you envision from reality. And again, there's no expectation that you do this perfectly. This is mostly for your information. How good are you at seeing something like this and plotting it? We really only care about quadrant 1, that positive axis, positive x, positive y. We're never going to have negative input sizes. So don't worry about any other quadrant. We have an approximation. Now I want to see a show of thumbs. How confident are you in your answer? Very confident. I'm pretty sure when you reveal it, it's going to be exactly what I have. I think I have the general idea, but I'll probably be slightly surprised when I see it. And who knows? I took the best guess that I could. And again, this does not matter at all. There's no grade attached to this, solely just to get a sense of the level of intuition that we feel like we have as a class. So it seems like for the most part, there are some people who are more confident, there are some people who are sort of confident, and there are some people who aren't confident at all, which is kind of what I would expect. The goal, hopefully, throughout this is to build some of that intuition. So the answer on a scale from 0 to 20 on the x-axis and a scale of 0 to 4,000 on the y-axis looks something like this. First question I have for you. What do we notice? Yeah.
Solid line increases a lot more than
Yeah, so as we scale past the intersection point, the quadratic function, the 10n squared minus 5 is larger than the 100n plus 200. Would we expect that to ever cross back over?
No.
No? As we scale past an input of 20 down the x-axis, we always think that the 10n squared minus 5 is going to be larger than 100n plus 200. Yeah,
I mean, I would assume something like that squared is just a function greater than n. Right?
yes. Yeah, that is exactly what we're going to be getting into is when we start talking about orders of scale. It turns out that the order of a function matters a lot.
I feel like infinitely larger than because, or is that am I thinking?
As the x-axis grows to infinity,
Yeah.
there is no bound on the number of times larger one is than the other.
Yeah.
Yeah. So we see that when n is less than 12, the 10n squared minus 5 is faster. For any n greater than 12, and not just up to 20, we can continue this forever. The 100n plus 200 method is faster. At exactly 12, they have the same performance. So if you're ever curious about this, you can go use any graphic software to graph it out. The important part is being able to find that expression. And you will eventually develop an intuition for what's larger, what's smaller, and where. The scale here is very important though, and this is something that I find a lot of people struggle with out of something like high school and before you have a ton of experience in college. Think about what the prior graph looks like if instead of scaling from n equals 1 or n equals 0 to 20, we scaled from 0 to 6 instead. You get something that looks like this. To the untrained eye, it looks like one of these is just better than the other. And it takes understanding of rates of change and recognizing that, wait, this x-axis here stops at 6. What happens as this scales? People don't ask that question enough. So you could draw some kind of conclusion like the quadratic function is always better than the linear function. Even though we just saw that that stops being the case at n equals 12. What evidence do we have we should be thinking of a different scale? What evidence is actually here that we could look at and say something seems fishy? Yeah.
Mainly you want to look at the fact that one of them is sloping, the other
Yeah.
is a like perfect straight line. Or there's a curve. Right?
Yeah. At a small enough x-axis, would we be able to even see that curve? No. So because we can visualize it, because we can see it, it's visually apparent. But you can think of if this were between 3 and 3.05, and we were just looking at that little sliver, it wouldn't look like even the quadratic function is, the rate is increasing at an increasing rate. One other thing to talk about, we're gonna start talking about these orders themselves. So one of the method one before was quadratic. It had an n squared term. The other one was linear. It had just an n term. When we have constants in our expressions, they are tedious to deal with, and they are almost always completely irrelevant to our perspective as computer scientists. Yeah.
So how do you derive the like mathematical function next?
Yep, we are getting to that in our next couple of slides. We're gonna get some examples of that and some practice with it. It's a great question, though. You're thinking ahead. We care about how these scale to large values of n. We saw just how fast an array list get versus a linked list get was even when we were doing it a million times when we were only looking at the 5th element. Computers are so fast that the only time we're going to notice something like this is if either the value of n, the value of the input, is really large, or if the function is a very high order. It's a very complicated function that requires a ton of work. Because of this, if we have two that are the same order and they differ by a particular constant, we actually, in practice, can ignore this for the scope of our analysis. We care about how things change when the input changes. If one method becomes faster and faster and faster comparatively, or slower and slower and slower comparatively, we say there's a difference in their running times. If there is a constant order of a constant change in their time for any input, then we say that they are the same order. Let's give you an example of this. So we have one method that is 100n, and we have another method that is 900n. It's obvious 100n is smaller than 900n. When n is 1, how many times slower is 900n than 100n? Nine times, right? If we were going to draw this out and figure that out, we would say we're going to compare the ratio of, we said this is 100 times n, but we're making a substitution of 1 for n. And for 900, it's 900 times n, but we're making a substitution of 1 for n. That is 900. Probably should have flipped these because the ratio here is just 9 to 1. This is going to take 9 times longer than that will for an input of size 1. Let's blow it up. Input size 1 million. We have 100 times 1 million. And we get 100 million. We do the same thing for 900. We get 900 million. The ratio is still 9 to 1. It's not changing as the input size changes. Because of this, we can state this is 9 times slower, and that never changes. What this also means is that the kind of problems that this can solve, this can also solve that. Yes, it will take 9 times longer, but we don't have a different point at which we really say, now we have a scalable problem that is unsolvable, or it's going to take so long to get an answer that we need to either find a more efficient way of doing it, or we just give up and say, we can't solve problems larger than this because it's going to take too long. So the first rule of orders of functions is drop constants. If we see something that runs in 100n, it is in order n. It is not in order 100n, and it is not different from one that is 900n. Those are both in order n. They have the same order because the ratios don't differ as we change that x-axis value, the input size, this n. Does that make sense? People have questions on that? When we design algorithms, we care about how the design scales for large input. So we really only care about large n. Even very inefficient algorithms work for small input. We are going to start classifying functions into orders. And the first piece of terminology, symbology that you're going to need is the concept of theta. Theta of f defines the order of that function. The function can't be modified, but the order of that function is going to strip away every aspect of the function that doesn't change that ratio. So each order in and of itself has an infinite number of functions that are inside it. Order n includes n, 1.01n, 1.001n, 1.2n, 2n, 10n, a billion n, 0.0000001n. All of those are in the same order because they only differ by that constant, what's in front of the n. Here we have very commonly seen orders in computer science. And we're gonna call this theta, big theta on the outside, so this is big theta of 1. You can shorten that to theta of 1 if you would like to. Theta of log n, theta of n log n, but let's take a second to analyze what each one of these are or what they mean. So first, they're listed from inefficient at the top to efficient at the bottom. And they describe how that behavior changes as n grows. As the input size grows, the size of the list, the number of operations that we need to do. Where we're going to be applying this in the very near future is to sorting. So I'm going to start thinking about and using sorting as an example as we talk about this. Is it easier or more challenging to sort a list of size 2 versus a list of size 1 million? Way easier to sort something of size 2. So that becomes the input. Based on the algorithm that we use, we're going to have something where the n is now this size of the list that we need to sort. So how does the complexity of the problem, the number of operations that we need to do as the computer, how does that scale as the size of the list changes that we need to sort? Any questions? How are we doing off of what we've seen so far? Have you set thumbs? How do we feel about what we're seeing? Okay. Gives me a pretty good sense of where we are, I think. Yeah. Yes, slides are up on modules of Canvas. I usually do it after I go over it. If you would like the slides ahead of time, because I often do a lot of examples and I will give you the example and then I will give you the solution, and either they're on the same slide and I reveal that, or it's on directly on the next slide if you're looking at it before class. If you would rather have that, I can share the slides repository with you ahead of time. But in general, just to make sure that people are going in blind to those examples, I post them afterwards, but I do recognize that people learn very differently. If having access to the slides ahead of time would be useful, send me an email. I will add you to the repository of slides. So let's talk about some of these orders. Theta of 1 says it does not matter how big the input is. It's going to take the same amount of time regardless of the size of the input. An example of this was the array lists get. It didn't matter if we were getting the second element of the list or the millionth element of the list. The time that it took to get that value is always the same. Something like linear now says that it will scale proportionally to the size of the input. So the linked lists get now has a number of operations, a number of nexts to do that is proportional to where it is in the list. You query something at index 5 and it's going to take you a small fraction of the time that it takes for index 1000, but it's going to scale at that same rate. The difference, the time it takes to go from index 5 to index 6 is the same amount of time that it takes to go from index 1 million to index 1,000,001. It's still a single next call. So that process is linear in nature in that it's always the same amount of time to do the next thing. How many of those do you need to do? That's what scales linearly. The total amount of time is going to scale with that input. Quadratic, we're going to see a lot when it comes to sorting. This is something like every time we go to the next element, we need to question something about everything that came before it. So the total number of question answers, imagine that we're all in a group playing a really annoying ice-breaking game where I say some weird fact about myself. The next person in line says some weird fact about themselves and repeats the weird fact that I said. And the next person says something about themselves and everything that has been said before them. That is something that is quadratic. The total number of facts stated is quadratic. You can think of it as n times n, or scales based on, for each element, we're doing something the number of elements times. Cubic is just n times n times n. For each element, we're going to do something the number of elements times the number of elements times. And then finally, we have 2 to the n. 2 to the n is exponential. It really should say exponential, and the one next to n log n should say log linear if you want to have names for either of these. We have log linear and we have exponential. Something that is 2 to the n scales worse than n cubed. It says that we're going to do 2 times 2 times 2 times 2 times 2 for each element. We're doing twice as much work every time we add an additional element to the end of the list. One other important aspect of asymptotic notation is if we, so I guess first we can say finally in constants. If we add constants, if we subtract constants, if we multiply by constants, or if we divide by constants, that's not going to change the order that it's in. The other really important rule is that if we add or subtract a function in a smaller order, that also does not change the function order. So, theta of 900 n squared plus 10,000 n plus 4 is equivalent to 0.00, I should say theta of 0.0001 n squared minus 100 n plus 2. Even though these look very different, they have an equivalent order. Because the way that we're going to end up doing this, the process we want to go through is remove all constants and remove all lower order functions. So something that is constant is lower order than something that is quadratic. We're going to get rid of it. Something that is linear is lower order than something that is quadratic. We're going to get rid of it. Same thing over here. Constant, linear, both of those terms are gone. Finally, we have multiplying by a constant value. So the 900 is gone. The 0.001 is gone. And what we have left is n squared and n squared. This seems incredibly unintuitive at this level because you will want to say these are very different functions. And they are. They just differ by a constant factor. Even if that constant factor is very large, you could say this will always run 100,000 times slower. And that doesn't matter as we scale because it's always staying 100,000 times slower, or it's capped by 100,000 times slower. There is a difference there, but it is dwarfed by anything where the order changes. As we get into large N, the fact that it's 100,000 times slower is going to be way different than even if there's a small change in the associated order. As N scales to 1,000,000, that's going to be way larger than 100,000 for any change in order. So that's why we care about that scale. What's the order of this function? Let's go here.
Theta n raised to 3.
Yeah. Theta of n cubed. We ignore everything lower term, ignore the plus 11, ignore the minus 4n, ignore the plus 2n squared. Those are all lower orders than n cubed. And finally, we ignore the constant on n cubed. So it is theta of n cubed. Yeah.
I might be misunderstanding here, but are we essentially saying, say I have another function that's 3n cubed plus 4. Are we saying those are eventually going to have equivalent efficiencies because they have the same order?
they don't scale differently enough to matter. Yeah. So one will always be faster or slower than the other. But as we get closer and closer to the order of magnitude, the order of size of problems that matters, that difference would be dwarfed by anything that changed in order.
Those lines in the graph get closer and closer.
Yeah, if you're staying at the same scale, then they don't diverge by more as the graph moves and gets larger. Or even if they do, the scale here is twice the size. It's always moving at, it's twice the size. The difference in ratio here between the x-axis and method 1 is going to be half the size of that of method 2, or even 10,000 times. Doesn't matter as long as it's constant and not changing, or capped by a particular value. Yeah.
So in these, you really just ignore everything except the largest, the m is the largest exponent.
Yep.
And then that data.
Yep. And we're gonna go into more detail that says there are some additional tools that we can use for these comparisons, but we're trying to strip out all of the unnecessary complication to be able to say how good and or bad is this solution.
Is it ever possible to get a fractional exponent for n?
Yes.
Okay.
That is very possible. In fact, I will have an example of that later on in this lecture. All right, time to get some examples. The last few minutes of class. We again have two competing algorithms. We're going to say algorithm 1 works at an squared minus b log n, and 2 runs at cn plus d. First question I have for you, does it matter what the values of a, b, c, and d are? No, those are just constants. You can replace them with anything and it doesn't change when we're comparing these two methods. Which one is better or worse from a computer scientist perspective? The associated orders of algorithms 1 and 2. Yeah.
The number 1 would be theta n squared, would be quadratic, and the number 2 would be linear theta n.
Yep. Theta of n squared for 1, which we will call quadratic, theta of n for number 2, and we'll call that linear. If they accomplish the same task, which should we do? Which should we use? Yeah.
The second one.
Second one? Second one will scale significantly better than the first one. Absolutely. Another example, here we have 1 and 2. What's the order of 1? What's the order of 2?
1 theta n cubed.
Theta n cubed is correct for number 1. Now number 2.
Theta n squared, right?
It is quadratic. So you can just go ahead and distribute the n, you get n squared plus n over 2. The over 2 is a constant. That can go away. The plus n is a lower order. That can go away. You're left with n squared. So it is quadratic. And in fact, we're going to see n times n plus 1 over 2 about 10 times in this class for different reasons. It's going to show up over and over and over and over again, and I'll talk more about it when it shows up again. So we find the order of algorithm 2 just by using algebra. The goal is to derive some function where you have each order added or subtracted from each other order. We don't want multiplication or division anywhere in there unless it's a constant. As soon as we have a variable multiplied by another variable, we have work to do. Variable divided by another variable, we have work to do. Two more algorithms. An cubed and n factorial. Let's start with a question. Can we think of an algorithm that runs in factorial time? Yeah,
Like something recursive that's increasing once each time it's called.
something interesting, okay. I think that will not quite work, and once we get into recursion, we can actually play around with that, for sure, yeah.
It's not similar to my thoughts, like you're gonna take a linked list and then copy it, but in reverse order. So swap, so you're moving to over that.
Yeah. That actually is only quadratic. It actually feeds into that n times n plus 1 over 2 that we saw on the past slide, but I'll get into that later. My go-to for this is BOGO sort. Has anyone ever heard of BOGO sort? It is the worst way to sort a list that exists. Here's how you're going to do it. Take the list, randomize it. Check if it's in order. If it's not in order, randomize it. Check if it's in order. If it's not in order, randomize it. Check if it's in order. Let's say we have a list of 10 elements. How many times would you expect to permute this in order for just the first element to be correct? For that to be the lowest value in that list? About 10 times, right? Because we're going to randomly select each time. That's going to be a distribution that's going to have an average of 10 times to get there. All right, so 1 in 10 times we're getting the first one right. Let's say we assume we get the first one right. Now there are only 9 numbers left in a 9 array. How many would we expect to get the second one in order? How many times should we have to do that? 9? There are 9 options. So now we have to get both the first one and the second one in order. So that is a multiplicative effect. So we have 10 times 9, 8 times 7 times 6 times 5, which is going to be our factorial. Have we seen just how fast factorial grows? It's ridiculous. Really, anything beyond the low 20s is not going to end really in our lifetimes. Beyond about 30 is going to take more time than the Earth has left, which is kind of ridiculous to think about. So if you identify any function that runs in factorial time, you can very quickly think anything larger than 30, just no. Not even in the realm of possibility. So we're going to discuss much more efficient ways to sort as we move on. But now we're going to transition to, and this is going to come back and we're going to do it tomorrow, but we're going to transition into how we're going to be able to analyze this from code rather than just from running or creating a program around this. So we're going to analyze the code rather than run the code. We're going to look at the code and try to figure out what is the order of magnitude. How is this program going to scale for different sizes of input based just on the code that's in front of us? How we're going to do it is we know that programs are made up of operations, and those operations are instructions to the CPU. So we are going to count how many operations we are requesting of the CPU with respect to the input size. So if we could go through and count them, then we could plot that. When the input is size 1, how many operations? If the input is size 2, how many operations? If the input is size 3, how many operations? For each of those operations that we see, how many times is that going to be executed throughout this program? And then we're going to abstract that into the input size. So maybe this runs n times, where n is the size of the input. We're going to start being able to create those variables and analyze the structure of the code. There are certain constructs, programmatic constructs, that make this a little bit harder. What happens if we have a conditional? What happens if we have a loop? What happens if we have a method call? Or even worse, a recursive method call? We'll talk about recursion later and tie this all to that later. But in the meantime, we can ask, something about the linked list size method. So let's just start here real quick. How many operations are executed for a linked list of size 1 when we are determining the size? Yeah,
There needs to be one that's list getting the size.
yeah, we stored it as a field, right? We're always adding to or subtracting from it. So calling the size method is reading the size field. So when the linked list of size 1, it's a single access. It doesn't matter how big the linked list actually is, it only requires a single operation to figure that out. So you can now see that this is an example of a function that is theta of 1, it is constant, it doesn't depend on the size of the list. If we didn't have that field and to figure out the size, we actually had to iterate and count the nodes. That would be a little bit of a challenge. But it would change it from something that is constant to something that is linear. Because now based on the size of the list, we would need to be asking next, 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 that many times. We'll come back tomorrow and we'll actually look at real code examples and try to plot out their running times by analyzing every line of code that we have. So I'll see you tomorrow for that. I have office hours starting now. If you have any questions about what we just covered, the homework, getting started on the homework, we're stuck on the homework. Let me know.